Hi friends, now we will discuss on the topic hydrogen production from natural gas. In the last classes we have discussed on the utilization of natural gas, and we have seen that it can be used through the conventional route for electricity production, or it can be produced to used to produce syngas and further liquid fuels, and it can also be produced to hydrogen. As you know that hydrogen is considered as as a green fuel and the future fuel also. So, in this class we will discuss on this content, the hydrogen as a green fuel, then hydrogen production routes, then natural gas as a feedstock for hydrogen, and the routes for hydrogen production from natural gas. There are reforming and decomposition of methane. So, as you know that hydrogen is having very high energy density and heating value is 142, high heating value is 142 megajoule per kg, and we also know that hydrogen can be combusted when there will be no carbon dioxide emission. And one important feature of hydrogen is that it can be used in fuel cell and electricity can be generated. So, here this figure shows us the electricity generation in the hydrogen fuel cell. So, when hydrogen is used as a fuel in this fuel cell, where in the anode this hydrogen is coming, and then in this here it is converted to H plus and E minus, then H plus is transported from anodic to cathodic chamber through this membrane, hydrogen transfer membrane, and it is coming to this cathode where oxygen is supplied. So, oxygen reacts with H plus and E minus. E minus or electron which is generated here in the anode, it is transferred through the external circuit and comes here, and then this electron and then H plus which is transferred through this membrane, and this oxygen reacts and converts to H2O. As a result, what we get electricity here. So, it is electricity is the very cleaner mode of energy, that is why hydrogen is considered as the green energy. So, this hydrogen can be produced from different resources, and we will be briefly discuss that. So, this can be produced from reforming of hydrocarbons or biomass and gasification of carbonaceous feedstock and decomposition of hydrocarbons like say methane, then thermolysis of water, electrolysis of water, photolysis, and then dark fermentations and microbial electrolysis. So, these are the different methods which have been reported for the production of hydrogen, and we will see the comparison of these processes. So, reforming process, as we know that it may be of different types, just we have discussed in the previous class. It may be autothermal, it may be steam reforming, it may be dry reforming or dry reforming, anything it may be, and we will be comparing those things. Say here steam reforming, partial oxidation, autothermal reforming, plasma reforming, biomass gasification, methane catalytic decompositions and coal gasification. And if we see here, these are the different feedstocks, some are hydrocarbons, biomass and coal, and the efficiency for hydrogen production is also different and maturity level is also different. And some other examples are say biomass reforming, plasma cracking, liquid phase reforming, thermolysis, electrolysis and photolysis. So, if we compare, we can see that either hydrocarbons or biomass or coal or other carbonaceous materials have been used for the reforming process, and the efficiency is also different, and most important is that their maturity level. If we see someone very few are in commercial scale, all are in maturity either long term maturity or medium term or under development. So, these are the different technologies which are available for hydrogen production, and the commercial process are reforming and then biomass gasification and then coal gasification, and here we are having electrolysis. So, basically if we see the methods, then we will be having some important data, that is the steam reforming partial reforming that captures maximum share for the hydrogen production, followed by gasification of coal and biomass, and then electrolysis, and others are very less, contribution of other processes are very less in commercial scale, they are under development. Now, we will discuss on reforming, because it will be using hydrocarbons and basically in our case it is natural gas. So, natural gas methane we will be converting to hydrogen through the reforming processes, and different reforming processes are dry reforming, steam reforming, partial oxidation, autothermal reforming and dry reforming. As we have discussed in the previous class and as evident here also, we see H2 by CO ratio is maximum in case of steam reforming. As we are interested to get the hydrogen through this route, so obviously the steam reforming can be a more suitable route for the hydrogen production. So, we will be discussing some more on steam reforming, and already we have discussed other reforming in previous class. So, in steam reforming, steam is used for the reforming purpose. So, this is our say hydrocarbon and then this is our steam, it will gives us NO and H2 rich gas, and this is del H value. So, what we are getting here? So, if it is a C1 then N1 then it is methane, it is representing methane, and then SMR reactor it requires steam. What will be the ratio of the steam and methane? That is very important, that is it requires S by C, steam by methane ratio as 1:1, and if we give more steam and more S by C ratio, we can get more hydrogen. And SMR has efficiency of around say 70 to 80% and carbon dioxide emission is 7 kg carbon dioxide per kg of hydrogen produced. And in this case catalyst, as we have discussed in the previous class, that nickel based catalysts are used. So, mostly used, but other catalysts are transition metals, that is iron, cobalt, nickel, copper, and the noble metals, these are have been reported, and these are the active ingredients for the catalyst and some support is required. So, basically gamma alumina, CaOL2O3, MgO, MgAl2O4 and TiO2, ZrO2, SiO2 have been used. Among them these are very commercially available. So, this catalyst also coke deposition is a problem for this catalyst, and if sulfur and halogen compounds may also deactivate the catalyst. And some industrial catalyst suppliers, if we see, that is Baden, Aniline and Soda Factory, BASF, Haldor Topsoe and United Catalyst, these are the players for the catalyst supply in commercial scale for SMR. Now, we will see the mechanism. What is the mechanism for the production of hydrogen through this route? So, we have hydrocarbon, then we have steam. So, steam and we have some catalyst. So, it is gas and solid phase reactions. So, we will be having steam, so that steam reacts with surface nickel atoms which is available in the catalyst, and then it forms adsorbed oxygen atoms and gaseous hydrogen. This is the first step, it is assumed. So, H2O it is in the support of the catalyst sites, the nickel sites, it is giving us H2 plus OS which is adsorbed. Then again methane we have also. So, methane reacts with surface nickel atoms and then it yields CH2 radicals which is adsorbed and adsorbed H atom. So, CH4 with catalyst site, it is giving us CH2 in adsorbed form and hydrogen also as adsorbed form. So, these adsorbed radicals and H and O will further react. So, we will see here the adsorbed radicals and adsorbed oxygen react to yield adsorbed CHO. So, this is the reaction CH2S plus OS, it is giving us CHOS plus HS. Then CHO which is adsorbed, that can also be converted to other forms So, as mentioned here, there may be possible that CHO is converted to COS plus HS, adsorbed COS and adsorbed hydrogen, and COS with adsorbed oxygen, that can give us CO2 adsorbed plus sites, and then CHO adsorbed can react with oxygen or adsorbed, and also it can give us CO2 adsorbed and hydrogen adsorbed. So, these are the different species which are generated during the process in the catalyst, and then those with the help of the catalyst and these intermediates, that COS can give us CO and the sites, and then CO2S can give us CO2 and sites, and HS can give us H2 and sites. That means, after desorption of those gas, the sites are made free. So, catalyst is now free, our feedstock is converted to product, and that is fuel of rich of hydrogen and carbon monoxide, also having carbon dioxide. So, this is the mechanism of the SMR reaction. Now, we will see how the natural gas can be processed through this route. So, here we have say natural gas. So, that natural gas certainly will have some sulfur, and that sulfur will be the poison to the catalyst. So, we have to remove it. So, for this removing, we are using hydrogen here. So, desulfurization unit DSU as the first step for the process. Then some catalyst are used, that is cobalt molybdenum catalyst COMO catalyst, and then it is 290 to 370 degree centigrade, and then this is your catalyst bed. Then zinc oxide bed is also used as an and then alumina guard. So, these are the series of oxides are used, and in which the DSU reaction is taking place, and H2S and halides are separated from the natural gas. The natural gas will be going to now reformer SMR, and before going to that, it is gone through the pre-reforming step to raise the temperature from 290 to say it is up to 525 degree centigrade, and then it will be going to SMR reactor where the temperature is higher, that is 800 to 900 degree centigrade. So, here after this SMR reactions, so CO and H2 gas will be there. So, there will be some shift reactions to produce more hydrogen. So, high temperature shift water gas shift reaction is taking place here with the help of FeCr2 catalyst at 340 degree to 360 degree centigrade, that is a high temperature water shift reaction with the S by C ratio 2.5 to 3. Then we will be getting more hydrogen rich gas, and that will go for pressure swing adsorption for the separation of hydrogen, and then the rest of it, sum of it is going to low temperature water gas shift reaction, and here FeCr2 catalyst and 2.5 to 3, that is S by C ratio. Then it is going for carbon dioxide absorption. Then after SMR, it is going to shift reaction. It may be at a high temperature water gas, or it may be at low temperature water gas reaction, and then after that it is going for carbon dioxide separation, and then we are getting 97 to 99% purity of hydrogen, or here we also get PSA through the pressure swing adsorption, we can get the 99.99% purity of hydrogen. So, then we will see how the PSA works. So, pressure swing adsorption works to separate the impurities present in the hydrogen, and different types of adsorbents are used for the separation of different types of impurities in the gas stream, like say silica gel, activated carbon, molecular sieve and activated alumina have been reported, and these components are suitable to remove different type of impurities like silica gel for ethane, propane, butane etc., activated carbon for methane, carbon dioxide, and molecular sieve for methane, carbon dioxide, nitrogen, and active alumina for water. So, these are the different adsorbents which are used for the separations of the other gas components. So, here we use the feed gas hydrogen plus impurities at high pressure, then it is going through different adsorbent beds, and we are getting hydrogen rich gas here, and this is our tail gas, hydrogen lean gas. So, there is less hydrogen in this gas stream. So, this PSA works in a cycle. So, if we have some adsorption first. So, gas adsorption takes place in this case, then depressurization takes. So, high pressure pressurized gas adsorptions, then we are depressurizing it and then purging it and again repressurizing it. So, it has some cycle, and the different operations have certain span in the whole cycle. So, this is the way the hydrogen is produced from the natural gas through steam reforming. Now, we will discuss on the methane decomposition, how the methane can be converted to hydrogen through decomposition. So, this can be done, the decarburization, dry natural gas cracking is a promising alternative and carbon free technology, and this can be converted to carbon, solid carbon plus hydrogen as per these reactions. So, del is 75.6 kilojoule per mole, and these reactions requires high temperature. It is around say 1200 degree centigrade temperature is required, because the carbon and hydrogen bond is stable bond, and so break it. So, it requires high temperature, and in this case carbon dioxide emission from burning of process fuel, that is your methane, is around 0.05 mole CO2 per mole of hydrogen, which is very less with respect to that used for SMR, that is equal to 0.43 mole carbon dioxide per mole of hydrogen. So, these things, methane to carbon formations and hydrogen production, it is a thermal process, and but it is difficult to perform without the presence of catalyst. So, use of catalyst reduces the temperature from 1200 to say 500 degree centigrade, and different types of catalyst can be used, and for this the reactor configurations may also be varied, fixed bed to fluidized bed. People have used fixed bed reactors and alternating between different conditions, or a fluidized bed or regenerator combination they have used. Out of these two reactors, the fluidized bed offers the flexibility and ease of continuous operation. Now, if we think about the methane decomposition, then we can get different methods. One is your thermal cracking, another is your catalytic methane cracking, or we can get plasma cracking, or we can get molten media cracking. So, this thermal cracking, thermal black process, advanced thermolysis, and this is catalytic methane, metal catalyzed and carbon catalyzed cracking, and here plasma cracking, thermal cracking and electrochemical plasma, and here molten media cracking, thermal molten media and catalyzed molten media. So, these are different types of methods people have used for the production of hydrogen by the decomposition of methane. And now, we will see the thermal cracking. As we mentioned that it is a thermal process, we have to apply heat, and around 1200 degree centigrade the methane will be converted to carbon and hydrogen. But as we mentioned that it is the endothermic process, and also it is not that efficient, the high temperature requirement is there, and this temperature can be reduced by application of catalyst, and then it will be termed as your catalytic method, not a thermal one. Thermal cracking of methane, the first industrial implementation of this thermal cracking of methane was initiated by the European Commission as this Solheim curve project in 2009 to produce hydrogen and carbon black, and in this project the solar power reactor with capacity of 10 kilowatt was tested for a temperature range of say 1467 to 1997 degree centigrade and a pressure of 1 bar, and the 55% energy efficiency was achieved. So, the major problem in continuous operation of thermal cracking of natural gas is the plugging of reactor due to the carbon deposition. So, then the catalytic methane decomposition developed, and in this case the temperature requirement can be reduced from 1200 degree centigrade to 500 degree centigrade, and different types of catalyst have been tested as shown here. You see nickel based, iron based, carbon based catalyst, and then these are some other catalyst, and this is your say non catalytic decomposition. So, when we are not using any catalyst, our requirement is 1100 to 1300 degree centigrade, whether we are using the catalyst, the temperature requirement is decreasing, and ultimately we are able to get the 500 to 700 degree centigrade by using nickel based catalyst. So, that is the advantage of the use of the catalyst, and when we use these different catalyst, the type of carbon which is deposited on the catalyst bed is also different, we see here. So, for this nickel based catalyst we can get carbon filaments, for Fe based catalyst we can get carbon filaments, for carbon based turbostatic carbon and carbon filaments, and here graphite carbon and turbostatic carbon we can get. So, different types of carbon can be formed by this way, and obviously the transition metals have been used for the production of catalyst, and nickel based catalyst is having more capacity to get the cracking at lower temperature. Then plasma cracking of methane. So, as you know that plasma is a ionized gas, and it can be produced at high temperature, and this can be used for the cracking of the methane also. So, based on the method applied to generate plasma and the temperature difference between the electrons and heavy particles, the plasma technology is classified into two types. One is your high temperature thermal and non-thermal. One is thermal by using high temperature, and another is your non-thermal, the electrochemical plasma. So, two types of plasma we can produce. So, out of these two, if we use a thermal plasma, the temperature will be very high, and it uses an electrical power of around 1 kilowatt, and the reactor attains temperature of around 5000 to 10,000 degree centigrade. So, use of this technology is not possible for this case. So, the non-thermal electrochemical plasma can be produced and used for the conversion of this methane to hydrogen, and in this case the temperature is around 350 to 750 degree centigrade. And this plasma cracking of the methane has some advantage also. It has high thermal efficiency, it has high purity of hydrogen, and simultaneous production of valuable byproduct carbon, and very low carbon dioxide emissions. So, these are the advantage of this, but the consumption of relatively high electric energy in plasma process can make this apparently uneconomical, and make their applicability restricted to large scale application. Then molten salt media cracking of the methane. So, people tried to get the high temperature of a molten salt media to crack the methane, and when the carbon is produced by the cracking of methane, that carbon is also lighter than the density of the molten salt. So, it can be go up and can be easily separated. So, here we see methane is coming from the bottom. So, this is our molten salt. So, here the reaction takes place, gas and liquid phase reaction, then carbon is formed and hydrogen is formed. So, hydrogen as a gas it is going out, and carbon as a solid it is floated, as the density of carbon is lesser than the density of the salt media. So, carbons will goes up and it will be separated from the top. So, this is the mechanism through which carbon is separated from the salt media. This technology offers the opportunity to operate the hydrogen production reactor in continuous mode, and deactivating of catalyst is eliminated there. There is no chance of deactivating of catalyst, and the compatibility between hydrogen, carbon and molten media, and the stability of molten media at various temperature ranges will be the major challenge for this process, and presently this technology is under development. So, we have discussed different types of processes which can be used for the production of hydrogen from the methane or the natural gas, and once we can get hydrogen, that can be considered as a green fuel. So, up to this in this class, thank you very much for your patience.